Okay, in the last video, I just described some of what tokens would do and didn't really have anything set in stone on how a syntax, or at least the grammar, would look like. So today, just going to talk about CIL. It's the intermediate language used in Microsoft's Visual Studio compilers, Visual Basic, C++, and C#. And I'd go over all the commonly used operands used in that intermediate language. So I have it all typed out that I got from a textbook, and I'm going to go through all the commonly used operands that a programming language gets broken down into, particularly Visual Basic, C++, and C#. So the first few ones, you have add. Add basically is that you have two values and you're adding them together, returning a result. The OVF just means that there's an overflow, and with the UN means that you're using unsigned integers to do the addition. So add two unsigned integers with overflow. And is bitwise, like a register keyword. So it's bitwise and. So it's one value and another value. Arglist, return argument list handle for the current method. So now we're getting into branching, and there's a lot of branching, especially if you're getting into conditions, conditional branching, if, then, else, else if, while, return statements, stuff like that. So if you have a piece of code like this in CIL, Microsoft's Common Intermediate Language, and then you have, that's typically how it would be written, like this. And what the BEQ means here is that software, a program, will branch if it's equal to any given value that you specify. You must specify what that value is. BEQS, branch if equal, short form. And that's if you're using something like, if you're working in C# and you're using the S byte, right? Like an 8-bit mini integer. Otherwise, it would just be a 32-bit integer. So there's that. And a lot of the branching will use the same idea of operands. So BGE is branch if the target is greater than what you specify. And same thing here as before. If it's a short form, if you're dealing with an S byte mini, otherwise it's a 32-bit integer. Branch to a target greater than BGE.UN, branch to a target that's greater than what you specify, unordered. And BGE UNS branch to target greater than what you specify unordered short form. And it's turtles all the way down. It's the same thing. It's all the same. The only thing that's different is the meaning and the operation that's performed by the operand. So branch to target greater than what you specify. Branch if less than. Oh no, sorry. BLE, branch if less than or even, and BLT is branch if less than. That's it, just less than. BNE, I forgot what BNE is. Okay, BNE, branch to a target if the target you specify is unequal or unordered. Box. It's been a while since I did this. I get the gist of it, but with box, this is actually type token. Convert a boxable value to a boxed form. If I remember correctly, from C#, you can convert assigned 8-bit or 16-bit or 32-bit up to assigned 64-bit integer value. And I think this is what's happening here. Unless I get my textbook out and verify that, because I just wrote down a brief description of what it does. Then you have the rest of the branching operands. Just a straight branch if branch with a short form. Break. It says break informs the debugger that a breakpoint has been reached. So now you have BR false and BR false S. Branch to target specified if it's false. BRINST. It says branch to target if value is a non-null object reference, and then the short form of it. So BR null, branch if target is null, branch if target is null, short form. Branch if target is true, BR true. Branch if target is 0, and branch if target is 0, short form. Now call method. Call method is really special when it comes to CIL. With CIL and how it pertains to the Visual Studio is Visual Studio is supposed to be thought of as a huge API rather than like it's a compiler, but it's a huge API too, and you can call any method that's been defined in its libraries, whether it be for manipulating strings, regular expressions, from a networking stack, graphics, that sort of thing. Call site descriptor. So call the method indicated on a stack with arguments described by what you hear, and this is, you can put your own method that you want to describe. Cast class, you can cast a variable, I think it's a variable, Cast an object to a class. CEQ, check if target is equal. Check if target is greater than what you're describing. Same thing here. CGT UN, check if target is greater. Unordered form. CK infinite, check if your, and that just means check if your 32-bit integer does not exceed the range of 32-bit integers. More specifically, it's going to throw an arithmetic exception if the value is not, if the 32-bit integer is not a finite number. Check if target, CLT, check if target is less than, and check if target is less than unordered. Constrained, what that does, it will call a virtual method on a type constrained to be a type T. I think it's a dictionary method. Now we get into conversions. Now what I described earlier, when an 8-bit integer is converted into 16, a 32, or 64-bit signed integer, these operands will sit there and do just that. So dot I, what did dot I do? Just as is a generic conversion, just converts into a native int. But now it converts CUNV.I8 just converts to a 64-bit native int. I4 will convert it to 32-bit native int, native integer. I2 will be 16-bit. I1 will be 8-bit, or specifically int 8 for you C# people out there. Might work with C++ as well. It's been a while for C++ for me. So same thing as before with the OVF. It will convert to a native int with overflow checking. CUNV, OVF, UN, convert to a native int with overflow checking. With an exception to an overflow. Unsigned int. Okay. It's a little different. It's going to be, the native int is going to be converted to an unsigned integer. And I1, it's a little bit different. So same thing with converting the native ints, the native integers from 8-bit, 16, 32 into 64 bits with this operand right here. When you have I1, so it's converting into a native 8-bit or I2 16-bit, I4 32-bit, or an I8 64-bit with overflow checking. And the reason why overflow checking is done is if you're writing software and you describe an 8-bit integer that's actually larger, or okay, if you're writing software and you've described a 16-bit integer and you try to put it, if you try to convert it into an I1 8-bit integer, it's going to tell you, no, you cannot do that, asshole. Okay? You can only go forward. You cannot put a 64 integer into a 32, nor a 16, nor an 8. You can only put an 8 into a 16, to a 32, to a 64. Same with the 16 to the 32 to a 64, and the 32 to a 64-bit. The R means the same thing as these. You are converting a floating point number. Maybe a float, something with half precision. 6, 7, or 8, something with 6, 7, or 8 significant digits can be converted that way. Oh, there's different types of 3. Okay. So this will just be a generic floating point. This will be, R4 will be a generic 32-bit floating with 32-bit precision of type F. And this will be of 64-bit precision. So it's really going to be a precise number, but it's also describing a huge, not a huge number, but with a lot of significant digits. Convert an unsigned integer and an U1. I think I need to double check that. Okay, now we're getting into the unsigned integers. So before we had signed integers. An assigned integer is really the range of numbers that a programming language can support. But with an unsigned integer, it supports a large, kind of a bigger range of numbers that it can support. So U1, it would be U1, an unsigned 8-bit integer. C1v.U2 would be an unsigned 16-bit. With C1v U4 would be an unsigned 32-bit integer. And a conv U8 would be an unsigned 64-bit integer. And just an example, a signed 8-bit integer can hold integers, anywhere from 0 to 127, whereas an unsigned 8-bit can hold a range of negative 127 to positive 128. And that's just an example, and it works all the way up from 16, 32, and 64-bit integers. CPBLK is you have something in memory and you're copying it to another place in memory. It's just a straight up copy. Copy object with a type that you would define here within these brackets. Usually, like, same thing here, but it's usually um, no, I can't think of an example of how. Um, and this is what happens when you don't work with this sort of stuff in a long while. Div just takes two integers, divides them, returns a value. Same thing here with you're doing it with an unsigned integer. DUP, you're just duplicating an item. Two items, really. And after that is putting it on top of the stack. End fault means end clause of an exception block, end filter, and an exception handling filter clause, and finally, and the finally clause of an exception block. It'd be okay if you have a chunk of memory, it will just initialize, not really initialize, but you're setting a predetermined set of bytes in a certain range of memory to a given value. So this is initialize object with your value here. That's right. Initialize the value at the destination address in memory. And speaking of talking about memory, it's not like you can sit there and say, put a chunk of information, put data into, this memory address. The CIL has its own memory addressing technique. So jump, I'll give you an example of jump. So if I go like this, so if you're writing a program in CIL and you need to have a way to jump to another part of the program, this would be it. JMP, jump. Okay. LD ARG, load argument. So another example coming at you is if I were writing a program, I would go, so LD arg, as the program is being executed by the computer, and it's working through all the instructions, it would see LD arg, not 0, and that means an argument would be loaded on top of the stack. Then you can do whatever kind of thing you want to do. Like that's the correct way to go about it. Like, say if I wanted to do LD arg, then I can initialize an object right. Then I can go and, especially with LD arg 1 and 2 and 3 and whatnot, I can go arg.1, load another argument, put it on top of the stack, and do my second argument, and then go from there. And in the S, short form, load argument on top of the stack, short form. LD arg A. What does it say for LD arg A? Load argument numbered num onto the stack, and in short form of that. Then you have ldc.i4.0, and here you have ldc.i4.1 or .2 or .4 or .8 is you are pushing items onto the stack as opposed to popping items from a stack, removing it from a stack. So 0 just a generic integer function. So if you step up to 8, 16, 32, and 64-bit integers, yeah, that's right, will be pushed onto the stack. LDC I4 M1, you're pushing -1 onto the stack, which is different. You got to be careful because you have CIL is actually case sensitive as opposed to capital M1. You're pushing -1 of type int32 onto the stack. Short form. No, S is short form. S just pushes -1 as int32 onto the stack. So actually, I should actually go back and say that all these are being pushed as int32. I8 is being pushed as an int64 onto the stack. My mistake. R4 is being pushed onto the stack as a float 32. So float 32, and this is being pushed as a float 64 onto the stack. LDEM, so same deal, with 8, 16, 32, and 64s are loading elements with index on top of the stack. Load element with type native int at index on top of the stack as a native int. So whether it be a native 8, 16, 32, or 64-bit. And then, of course, you have your float 32 and your float 64s. LDE, LEM. Load the address of element at index onto the top of the stack. LDFLD, push the value of the field of the object on top of the stack. And LDFLDA, it pushes the address of the object. Address of the field of the object on top of the stack. And LDFTN pushes a pointer to a method. Really? Pushes a pointer to a method referenced by a method on the stack. Oh wow. I never knew that. With the LD INDs, you are just indirectly loading values onto the stack. So integers, floats, make references. Well, with ref or ref, indirect load value of type object ref as 0 on the stack. And with U1, U2, 8, 30, 8, 16, 32, and 64s. LDLen push the length of an array on the stack. And that just depends on the type. Well, maybe 8 bytes are reserved for that. With LDLock, you are loading local variables onto the stack. Those local variables onto the stack short form. And load LOCA, load address of local variable with index. And same thing, short form. LD null, you are loading a null reference onto the stack. Load a defined object onto the stack with LD obj. This should be LD LDS FLD. Yeah. Push the value of a field onto a stack. LD token. Convert metadata token to its runtime representation. Leave just means leave a protected region of code, or exit rather. Allocate space from the local memory pool. And like I said before, it's not like you can sit there and play with machine memory, right? CIL has its own special kind of memory. It's not too different from, you know, playing with machine memory. MKRefNA, you're making a reference to any kind of, actually no, I should push a typed reference to pointer of type class onto the stack. Mul, MUL, multiplying two integers, giving a result with overflow checking, unordered. NEQ, negate value, new ARR, create a new array with elements of type, new OBJ, allocate an uninitialized object or value type, and call the constructor. So that's, it calls .ctor. It call, and CTOR just calls the main CIL library where much of these operands are performed against. NOP is no operation. So if I go like this and go NOP, no operation will be performed on this line or anywhere in your program that you write. NOP. Not is bitwise not. So if you have an object, let's say 1, if you're describing two objects or classes really, not, like you're describing this item, not the other item, Same thing with OR. It's bitwise OR. It's either one type or other type. But I think describing all these register types would be for another video, for another day. Pop, like with before, it just removes a value from the stack. A lot of people would say you're popping a value from the stack. Ref any type. Push the type token stored in a type reference. REM. If you do division, this will show the remainder, any sort of division that you'll do, and REM UN remainder with an doing unordered. One unsigned remainder when dividing one unsigned value by another. Okay. RET returns from a method like from C. The C people will get this. Return if you're doing an if else if statements for branching, and return to the main part of the program. Rethrow the current exception. So you have now you have SHL and SHR. Just means you're shifting integers and left, you're just doing it to the left, you're shifting to the left, and R, you're shifting to the right. And with this, you're doing it with an unsigned integer. Yes, return as an integer. STArg. Store value to the argument numbered number, and do that in a short form. STELEM. Replace array element at index with such and such value. So if you have an array with an 8-bit or a generic integer 8-bit, 16, 32, 64-bit value inside of your array versus 32 and a 64-bit floating point. And with the ref, you're replacing array element with the ref value on the stack. This should be STSFLD. Oh no, STFLD. Replace the value of field of the object with a value of something else. With STIND, you are storing the result at a certain address. And as before, with CIL, memory addresses are not quite like memory or machine, like CPU addresses or main memory addresses. CIL uses its own. So you have 8, 16, 32, and 64-bit values. And of course, again, 32 and 64-bit floating point types. Replace array element with ref value on the stack. St-lock, you're popping a value. In other words, you are removing a value from the stack with these values. I should go further to say that you're removing these values from the stack and you're putting them into a local variable. With st-lock, S, you're doing all that short form. St, store an object, variable, store a value of type, and it should be like this. So you're storing a type of this into a local variable. Sub and sub OFE, you're subtracting two integers, one without, one with overflow, and doing so, that should be subtract with overflow on an unsigned integer. So that's subtraction. Switch, jump to one of n values. Tail, so if I went like this, that would mean the operation after this instruction would be terminated. It's done. Subsequent call terminates current method. Tail, yeah, I did that right. So yeah, that's right. Throw, you're throwing an exception. Throwing an exception. Oh, there's one that I forgot to put in. Another important one. Unaligned. The subsequent pointer instruction might be unaligned. Unbox and unbox any. Extract the value type from object to its boxed representation. So with box, unbox is doing the opposite. You are unboxing a method that you have called from the main CIL library. It's been too long. That's what happens when you ignore something for too long. Volatile. The subsequent pointer reference is volatile. And interestingly enough, Microsoft has deemed this operand here, to no surprise, dangerous. Can you guess why? And or, it's another bitwise operation, means exclusive or of integer values, returns an integer. So that's that. That's the end of it. So this is all of CIL. This is, of course, Microsoft syntax. But I wanted to show you something. Let me open a new window. And I'll open that file. I'm going to show you guys something. And I open that file. Where did I say I've written it down? What to pay for? Okay. Opcodes. This is going to blow your mind. Okay. Now, what I've just shown you is Microsoft CIL. This is the intermediate language for, like I said, the intermediate language for Visual Basic, C++, and C#, also for F#, for those kinds of people out there. Now, a lot of the operands I've showed you can be compared to C. C uses the same kind of operands, and they're, depending on the compiler that you use, I know GCC and TCC use the same thing. If I can drag it over. It's the same thing. Here's the proof. Notice anything? Here's NOP, no operation, LD arg, LD lock, ST lock, LD arg, loading arguments. Pretty fucking neat, huh? There's all the branching operands, operations. Load an indirect value onto the stack. Switch. Adding, subtracting, multiplying, dividing values. Exclusive OR bitwise. So that's that. No, I don't want to say that. Core syntax. Core token. So last video, I sat there and defined what the tokens would be. And then I started kind of playing around with syntax. What's my new language going to look like? I don't fucking know these people. So I think what I'll do is just play around with crap. And figure out later if it's grammatically correct or not. So what if I did something else? Okay. Okay. So I played a little bit. I played around with the idea of how I can invoke a library. Um, so see if I can just start doing it. For extern. Yeah, that's right. It's defined in another library. Um, what could I use in place of a define statement? Open, override, private, public, rec, return, slides. I didn't even think of that. Referencing a top level namespace. I could do that. But I fucking hate global variables. I really do. You like playing with fire, kid? I don't know. Use a global variable. I wonder if you can use more than one global variable. I've never had a reason to use global variables before. What the fuck am I doing here? Oh, okay. Core token, good for any ride. Um, so what I'm doing is, during the stage of compilation, I'll have a source file. So um, so later on, I'll have, this is just a, you know, like, here, I'll show you, this will be a freebie. I'll show you. I'll do it on this. semantic assembler, generator. I think that's it. So here, where I have defined names of the tokens, there's later on in a compilation, in the code optimizer, I'll sit there and define those tokens and what they'll do. Unless I have the right one loaded up. I don't know if I have the right one loaded up. Where is my... Could be... the fourth one. Third one? Could be the semantics of it too. No, that's not it either. But anyway, all the keywords, whether you're using, a byte or use short, or using public or private or anything, all of it has to have a meaning within within the compiler. And during the code optimization process is where I'll sit there and really sit there and define, where in memory those keywords are going to sit, how they're executed. I really thought it would have been that in here. Okay, so for each token, let me drag it over here. It's a little freebie for you. Bring it down here. So this, let me, where is it? So this is the part where each token is defined as code. For the undefined symbol, for define, so define, if I sat there and did this in a C language, you know, like that, define. Compile string, compile for opening files, the warning keyword right here, and if I go back to it, warning, so there's the source for the warning token, error, token, TOK error, TAK error, no abort, none here because I'm showing you two different things. Like this code is a different language than what this will become. ST error, set error function, error 1. Here's the printf command to print out anything within the command prompt or terminal, if you will. Okay. Grelock, don't have that in core, but B check, bounce checking, reserve, reallocate, here's one split path, dynamic array add, okay, and it refers to external library, well, source code that sits outside of what I'm showing you here, but I'm not going to show you too much on that. So that's basically how it's done. The tokens here is just the first step in the compiler. You're defining all the keywords. Every part in the syntax process you're defining as, you know, here, everything that I have in quotations will be defined and code will be written for these definitions later on in the compilation process. Okay.
showcase to give this place a complete makeover. Now the only thing that remains is to do something about the noise. That's where the Ultra Touch batting comes in. The bad news is that we've got some theories but no concrete ideas when it comes to how we're going to cover the inside of this room with it. The good news is that because you have to leave it out overnight to fluff up to its full thickness, it's pretty easy to find in our office. Our Antlion Audio Mod Mic 5 giveaway continues. We're giving away 3 Mod Mic 5s and a Hi-Fi Man Edition S Mod Mic combo. Enter now at the link below. Okay, someone put all this stuff in a pile. I gotta get it over here. Anyway, this insulation stuff that we're using is really cool. I was first put onto it when Mike from Silent PC Review was showing me how he built his anechoic chamber. It's made by a company called Bonded Logic.
Socks and sandals.
Set it apart from other insulation. So it's not made of fiberglass or anything like that. It's actually made of recycled blue jeans. So it's like, if you're into sustainability, then I guess that's cool. But it's also got awesome thermal properties and some of the best acoustic properties, both in terms of like dispersing sound and actually blocking its transmission. They actually make a ton of stuff out of this recycled blue jean materials. When I was talking to them on the phone, they actually mentioned to me that one of the biggest uses for this stuff now is actually shipping perishables, like food. So Blue Apron, a sponsor of ours, actually uses Bonded Logic's shipping material to ship, you know, like cold stuff that sits on your doorstep so that it doesn't get hot and spoil in the sun. Pretty cool, right? Check this out, check this out. If you didn't believe it's made of recycled jeans, there's a piece of zipper. That's awesome. Okay, so right now what we're doing is we're getting a baseline measurement of what the sound is like through this wall of the server room. So everybody quiet. It's about 42, 43 decibels. Pretty sure that says LS, right? We've got a couple of different tools to help us cut. We do have a hand insulation saw, but from what I've read online, one of the best ways to cut it is actually with a bandsaw. So we had tried to come up with a brilliant plan for using like some kind of a mesh or like a netting to keep it up, but we actually ended up settling on good old-fashioned nails. Hold on, I gotta get a hammer. So we'll start in the corner behind the UPS over there. Well, I'm also gonna need a lot more nails than this. Dang it, Bobby. Okay, I'm clearly gonna be better off pre-measuring this. Look, I'm new at this, okay? Actually, you know what? For this one, I should just go right up the wall. If this doesn't work, we don't really have another plan at the moment. This is looking like it might work. Huh, how about that? Okay, so just a few more hours of this, and then I'm good. Okay, this is a thick one. Wow, I'm going to go through a ton of nails. How many are in here? I don't feel like this is enough. Oh, damn it. Was that the label maker? We'll deal with it later. Oh, that's the steel. Good for security. Bad for putting nails into. Good thing we dusted the servers, right? We are ready to get our after reading. Okay, everybody quiet! And we have discovered a fatal flaw in our testing methodology. Because the room is way quieter, but we would have had to take our measurement from quite a bit closer to isolate the noise that comes from the room from the noise that comes from the computers that are here and the transformer over there. So I give up. Whatever. Mission accomplished. But boy, is there ever still a lot of work to do. So what I discovered very quickly when working with the Ultra Touch insulation is that it still sheds a fair bit of material, creating dust. For my freshly dusted servers, look at this keyboard. Look at this keyboard. Fortunately, I was one step ahead and I ordered like a custom air filter, but we need a longer term solution. So that's where this special black stage cloth comes in. If we can cover up all of the insulation in here, we'll be able to keep this place from being a dust mine. Let's get crack-a-lackin'. Holy crap, this thing is heavy. And expensive. This roll was like hundreds of dollars. This stuff is acoustically neutral, I believe is the term for it, and it lets sound pass through so it can be absorbed by the Ultra Touch. If we were to put plastic over it, we would actually get substantially more reflections. Where'd my tape measure go? This is the problem with any DIY project. So I've actually done a lot of the easy stuff along this left wall here. It only takes a couple of nails and staples actually to hold it in place. But now it's going to get a lot more challenging. So check this out. Standing right behind the servers, you can hear how loud they are. Standing right here, it's that much quieter. Cool, huh? Oh, nice. I think this is going to make it all the way into this corner. Perfect. Okay, I need my stapler.
Wow.
Another handy-dandy thing about this fabric is once you start ripping it, it rips in a straight line in both directions as far as I can tell. I need shirts made of this stuff. So everyone's back in the office now, though. It is a couple days later. So I can't afford to accidentally unplug anything anymore. Oh no, I pressed the button. Escape. But I didn't put duvetine behind the server cabinet itself, just because I figured if I'm running cables back there or anything like that, I didn't want to have something that is more grippy. Not bad. Okay. Finally, almost there. We've got all the insulation contained, and finally, the last piece from Proto Case arrived. So this is my custom vent for the door of the server room. Now, noise isolation relies on sealing up a room as much as you can. I'll open this later. Come here. And as you can see, I've got this just covered. But in the event that our air conditioning fails, we've actually got a thermostat here that's going to monitor the temperature of the room and kick on an auxiliary fan up there, so at least it doesn't completely bake in here. So Jake designed and Protocase created for us a custom shroud that we're going to cover this hole with so that the sound doesn't have a direct path out, but the air still has a way in. Ow, my elbow. It's metal. What do they expect to happen to it in shipping? No, I'm not angry they packed it well. Ow, my knee. Oh, my heat sinks. Would any of you watching this believe I'm not much of a handyman? You guys try cutting through 5-inch thick blue jeans. It's hard. Okay, just going at it upside down. Ow! Damn it. Oh no, where did all these screws go? I don't have time for this. There it is. Alright, come on in, Brandon. I think this hole is not optimal. I think we may have to cut back a bit more. Also, I have to remove some of my nails. Did he just hammer nails into a door? Yes. Yes, I did. And now I'm removing them with my bare hands. Oh. Damn, I was hoping to hook that up there. Yeah, okay, screw it. I'm going in. We're just gonna drill right through the metal. Ah! Cut myself on a drill bit. Okay. Here we go. Wait a minute. Oh, I installed them backwards. It's actually a very simple, kind of elegant design. Good work, Jake. So we still have to do this, then the duvetine, then the grand finale. Here we go. Acid test time. Aha. Nice. Wow, it's actually almost level too. Look at that. Awesome. So there's ventilation. And here is noise blocking. Ow. Home stretch now. You just gotta secure the insulation to the door and cover. Oh, we're so close. So 42 by about 90. So I want to secure this really well. People are probably wondering why I'm using nails for this. The answer's pretty simple. They're easy to remove. I'm sure it's wrong. I'm sure the internet is going to tell me why it's wrong. And then I'll know. So it's good. That's how we learn. By doing things wrong and then being corrected on the internet. I'm going to cut it sort of approximately, but smaller, and then just kind of fold it over. I will give you this, Brandon. This really is very cool fabric. Ow!
What the heck?
There. So theoretically, I don't need this anymore. It's all covered. You know what? I think the air filter on this thing is overkill anyway. I'm not gonna bother. Hey, yeah, okay. So, we're done then, right? The room is quiet. The room is clean. The cables are managed. And, fresh from its adventure in learning to be water-cooled, this export server is sliding
Water-cooled server.
back into the rack. There's nothing left to do, right? Ho ho ho. You underestimate me, my friends. RGB lighting.
Seriously?
Oh, this is RGBW. Chainable up to 3 meters. Okay, first I need to know if these are the magnetic kits. Oh, yeah, baby, they are. Okay, that's excellent. We've got a couple standalone power supplies because we don't actually want these to run off of the computers that are in here. Because the RGB always needs to work. I cannot wait. Oh, this is going to be sick. Sick, I tell you. I'm going to give some thought to cable management here, given that was the whole point of this bloody project. Okay, so we're just going to go straight into the wall. Realistically, these do not need to run off the UPS. Wow, it's amazing! That's what I'm talking about. Alright, let's see if I can hit both of these at once. Oh, yes! Ting makes it easy to spend less on your monthly
That's pretty
mobile
stupid.